The era of the AI whisperer is over. We no longer rely on manual prompt tweaking or finding magic words to unlock a model's potential. When you treat a foundation model like a conversational chatbot, you get unpredictable results. To achieve high-stakes reliability in production, we must treat the AI as a deterministic information processing engine. Today, we call this discipline context engineering. It is the specialized science of curating and structuring the exact set of tokens provided to a model during the entire inference lifecycle. We'll build an automated workflow. You'll structure multi-step reasoning topologies, deploy frameworks that optimize instructions, and generate statistical evidence of accuracy. Mastering this transition is the difference between building fragile conceptual novelties and deploying scalable, enterprise-grade AI systems. Let's look at the architecture. First, we have to unroll the computation. Large language models are autoregressive, meaning they generate text by predicting the next token based on previous ones. If you force the network to guess the final answer to a complex problem in a single pass, the probability of error increases. Standard chain-of-thought methodology forces the model to show its work step by step, but it has a critical limitation. A single logical error early in the chain often compounds into a completely flawed final output. We solve this using the Tree of Thoughts framework. This enables branching heuristic searches, which are computer science algorithms that allow the model to explore multiple solution paths, evaluate progress, and backtrack when it detects a logical dead end. This chart shows the performance gain. By searching through a tree of potential thoughts, we see a 65% improvement in success rates for mathematical problem solving compared to linear reasoning. Even with branching logic, language models struggle with precise arithmetic. To bridge this gap, we use the program of thoughts methodology. Instead of asking the model to perform calculations, we prompt it to generate a Python script representing the problem's logic. The script is executed externally, ensuring that the final arithmetic is handled by a deterministic code interpreter rather than a probabilistic model. Delegating rigid computation and heuristic routing to these external structures transforms the language model into a highly reliable reasoning engine. Once the reasoning structure is in place, we must abandon the practice of writing monolithic text prompts. Relying on manual semantic tweaks makes your system brittle and difficult to scale. The modern standard is to use declarative programming frameworks like DSPY. DSPY stands for Declarative Self-Improving Language Programs, and it allows you to define AI behaviors as modular programmatic functions. Instead of crafting conversational paragraphs, you define tasks using explicitly typed input and output interfaces. You dictate the logic and the structural goals, while the framework abstracts the actual text generation away from your workload. DSPY uses secondary judge models to run automated optimization loops. These models autonomously rewrite and refine the prompt instructions based on your training data to maximize performance without human intervention. Avoid the common mistake of hard-coding logic with deep prompt trees. Overly specific instructions create ambiguous decision spaces that often lead to agent failure. By allowing the framework to compile the optimal tokens for you, you ensure that the model's internal reasoning remains aligned with its pre-training distribution. Treating prompts as algorithmic parameters rather than static strings allows for seamless enterprise scalability. You can migrate across different foundation models instantly without rewriting your entire instruction set. The third step is validation. You must move past subjective qualitative testing. Simply reading a few outputs to see if they feel right is insufficient for maintaining a production-grade system. We replace intuition with test-driven development, or TDD. This is an engineering methodology where you define quantitative success criteria and automated tests before you deploy your code. For complex agent workflows, we use Langsmith to trace every step of the model's logic. Tracing allows us to inspect nested pathways and identify exactly where a reasoning chain breaks down. For retrieval systems, we use frameworks like RAGAS. RAGAS stands for Retrieval Augmented Generation Assessment, and it provides specific metrics to measure how relevant your retrieved data is and how accurately the model uses it. This dashboard is from PromptFoo, a tool that allows for batch testing. It runs hundreds of scenarios simultaneously to quantify precision, the accuracy of the results, and recall how much relevant information the model captured. These dashboards are critical for catching performance regressions. If an AI provider updates a model checkpoint invisibly, these automated benchmarks will alert you immediately. Continuous quantitative evaluation ensures that your application remains a stable, validated system rather than a dangerous prototype. When these three components, reasoning, automation, and evaluation, function together, you have built a complete autonomous data pipeline. This approach provides the technical foundation for an AI systems architect, shifting the focus from writing isolated instructions to designing integrated intelligent workflows. You now use branching reasoning topologies, automated declarative prompting, and rigorous benchmarking. Your final step is to implement prompt injection mitigation protocols. Prompt injection is a risk where user input subverts the model's instructions. A robust architecture must use output validation and input filtering to protect the system. The future of artificial intelligence relies on those who can move past conversational prompts and engineer the model's context with security and precision.